Greetings! Today we are going to solve a simple problem under the beam deflection using the double integration method. As what the topic suggests, this particular problem involves deflection of beams, the Euler-Bernoulli beam theory, the elastic curve, and the double integration method, which we will utilize to solve the problem. So that means we'll encounter or help recall some former topics, applications such as differential equations of curves, moment equations, static equilibrium, etc. Well, let's get to the problem. Determine the maximum deflection of the rectangular wood beam when it's loaded by two end couples. The modulus elasticity is 12 GPa. We are asked to determine the maximum deflection of the rectangular wood beam subjected to two end couples. The beam is simply supported, has a span of 3.6 meters, and is made of wood. And again, as we mentioned, modulus of elasticity 12 GPa. Rectangular cross-section, as we see here, 120 millimeter vertical and 160 millimeter horizontal. We are to determine the beam's elastic curve equation, maximum deflection, and maximum deflection value and its location within this figure. So for that, we will first determine the beam's resistance to bending, represented by the area moment I. Now before that, we have determined a while ago the length of the beam is 3.6 meters, the left end moment is 9.6 kilonewton meters, the right end is 6.6 kilonewton meters. See that they both rotate counterclockwise. Mention the modulus of elasticity and the cross section. Now we have the free body diagram. The graphics are just merely a mesh edited in. And now let's get back to the moment of inertia. As we see, its formula is the base times the cube of the vertical height all over 12. The vertical height is cubed because the beam will have to be, when bended, it will have to be bended vertically. So let's move on. The base, as we know, horizontal in the cross section 160 millimeters or 0.16 meters. The height 120 millimeters, aka 0.12 meters. Which leads to our answer of the moment of inertia being 2.304 times 10 to the negative 5 m raised to the fourth. Now let's move on to the support reactions. As with every material problem, we'll first see in this free body diagram that there are no vertical external forces acting on the beam. We can safely say that reactions A and reactions B, you have determined, can be equal to 0 for the vertical equilibrium. So we can first say that reaction A can be equal to negative of reaction B, stemming from the combination of reaction A, reaction B equal to 0. That's the equilibrium equation. Now, this of course connotates that the reactions indeed move in opposite directions. That's at least a good confirmation that we're on the right track. Let's head to the point A, the couple A. As again, we recall that both left and right couples rotate counterclockwise. Applying the rotation. When we apply a rotational equilibrium, as you see here, reaction B creates moment 2 at A. So the action B from reaction A, whose length spans about 3.6 meters, plus the reaction of the left couple, plus the reaction of the right couple. Once we combine every like terms and simplify, we can find out that RB will be equal to negative 4.5 kilonewtons. And because RA is equal to negative RB, well, simply put, RA will be then equal to 4.5 kilonewtons, positive 4.5. Now we move on to the bending moment equation, internal bending moment equation. Our next step towards a beam deflection equation. Reaction force RAX and the end couple on the right are combined to create an equation describing internal bending moment that describes the changes along the beam. So as we see here, MX, this is what we call the internal bending moment. As we have pieced up reaction A and B, reaction A is 4.5. This, of course, we have to realize for proceed further because they are indeed first. Their units are first in kilonewton meters. We have to first convert it into newton meter for anything else. So convert that 4,500, 9.6 kilonewton meters, 9,600 newton meters. Okay there. Now we will apply the equation from we have mentioned a while ago, the Euler-Bernoulli beam theory, the beam differential equation, relating curvature to internal moment. As we see, as I circle right now, elasticity and moment inertia times the second derivative of y respect to x is equal to the internal bending moment. So, we determined the internal bending moment equation a while ago, which we are enlightening right now. Now, you remember the whole double integration method that we have mentioned earlier? We will then use that here. To obtain the slope and the deflecting equation, we'll use this double integration method by, you guessed it, integrating this equation twice. So, the first integration that we will refer to as the slope equation, because we'll see the element dy over dx, which commonly known since then as the slope. We will integrate it again. For that, this will be our slope equation. As you see, elasticity, moment of inertia, dy over dx at slope equals to 2,250 x squared minus 9,600x plus c1. Don't forget the constant integration. That's how we will know that indeed during the operations that we have indeed performed integration. Let's not forget that it is imperative that we do not forget the symbol. And as we see, also the slope equation for a problem. Moving on, and as we just stated, we will integrate it again to get the deflection equation. In this case, y will serve as the beam deflection. And as we see, highlighted 750 x raised to 3 minus 4,800 times x raised to 2 plus constant 1x plus the second constant. We have indeed integrated the constant once again. Now we'll move on to the boundary conditions. As we remember, the figure we have illustrated a while ago. Let's scroll back. This is a simply supported beam. And for that, we have to assume that deflection at these supports, either here or here, is 0. Thus, when we put in that x, that at origin, we can merely say that the constant 2 for deflection will be 0. But when we factor in the span of the beam itself, 3.6 meters, well, the whole deflection equation, as we see here, as we substituted 3.6 meter, the span of the beam, into the deflection equation, You can see a process right here. Step-by-step process. 34,992 minus 6,208 plus 3.6 first constant plus negative 27,216. Now transpose, then divide by 3.6, and down we'll get the constant 1, 7,560. Now, indeed, we have already determined C1 and C2. We can substitute it again to the final deflection equation. See here, since we have substituted already, C1 turns to 7,560, as we just got. C2 is what we got to be 0. Now, because we've determined the constants, we can also say that it is indeed the elastic curve equation. Unlike the other constant. Now we just need the location of the maximum deflection. Remember the slope? To know maximum deflection, we'll use the for this particular problem, we will use the quadratic method to find the equation's new roots. Since we have obtained the slope equation earlier, we will use the quadratic method to find the roots. Find the roots, which we will use to find the location of said maximum deflection. As we recall, this is our slope equation. Since we have recently obtained the first constant, we'll just plug it in there, and this merely simplification of this equation. And indeed, for this particular solution, we will find the roots of this slope equation using the quadratic formula. Let's not forget, this is the all and ever useful quadratic formula, very useful in getting roots. And you must remember, b here is the coefficient in the technical issues. B here is negative 320, A is 75, and C is 152. As we have to see, that's B, negative 320, A 75, and C is 252. Now we do the operations. No, don't forget to properly put in decimals. For this particular solution, we'll have to consider the full value of the decimals. Though typically it is still recommended that you write in full even in solutions and givens. So that's just claiming that for this particular solution, we did not skip or even say summarize any values during solving. So to ensure that we can be on the same page or have less discrepancy on the way. So, of course, since we are indeed getting roots, we have to consider this operation right here, plus and minus. So when we use the addition, this is going to be our result. And when we utilize the subtraction, and this will be our result. Now we indeed have obtained these values. We can substitute each of them to the, once again, deflection equation. Notice how the deflection equation is going to be very widely used here. So, alright, again, at x equals x to 3.22, we'll summarize it as we vocalize it, but it's there. That indeed is the root that we have obtained just a while ago. Though it is rather quick, you can simply straight up calculate this without any expected discrepancy per se. So as you can see, the resulting deflection is in the negatives. Alright, so we'll move on to the next one. The other root to be obtained, 1.04. And we can put it straight into a calculator, plug it in, which will result into this value, 3514.377371. And as we can see, this indeed is the larger deflection value. So, as verdict, the larger download deflection occurs at x equals 1.04, 1.04. And we have seen that the downward deflection sorry, is at 3514.377371. Okay, so remember the moment of inertia that we have obtained earlier? Yeah, we will then go back on some computed values. Moment of inertia and the given that we've determined earlier, the modulus of elasticity, in order to compute the flexural rigidity. The final component we need to finally solve for maximum deflection. See here, right? So you see here, modulus of elasticity and the moment of inertia. Just remember, all right, this is important. Sum this up. But right, you must remember to match the units. So when originally, as we see here, 12 GPa will be converted into 12 10 to the 9th power PA. Let's not forget the units. Let's make sure that they match, or at least if they'll match, make sure that they'll make sense on the final answer. Because once the units are wrong, obviously, that's still a providingly wrong answer, or at least an answer that makes less sense in hindsight. So, we determine it. As we have determined earlier, the moment of inertia is 2.304 times 10 to the negative 4, times 10 raised to negative 5 with meter to the 4th power. So, as you see here, simple multiplication job, we obtain 276,480 meter cube kilogram second square. Alright, now we can proceed indeed to solve for the maximum deflection, as it is obtained with this formula right here. Maximum deflection equals to the flexural the maximum deflection over the flexural rigidity. As we see here, this is the flexural rigidity that we have obtained earlier, and this is the downward deflection that we have obtained from here. Because it is the larger down deflection. So, as computed, the result will be 0.0127 meter. We note that this is in meters, so unless required, we must still, again, don't forget, convert to the unit that is needed. Though it is not necessarily needed for this particular problem to know what unit it is, technically, the given cross-section is by default in millimeters. Yes, it is. So, by virtue, we will have to also put it in millimeters as well. So we move decimal places. 1, 2, 3. There we go. The maximum deflection, 12.71114501 millimeter. And simply put, the highlighted values are all we need to solve. The location of the downward deflection and the maximum deflection. Indeed, from this, we have obtained the needed values of maximum deflection and its location. And we note that the The span of the beam is 3.9, 3.6 meters. Sorry. So we can simply say that this half is 1.8 and the other half here is 0.9. So just inch it a bit from the half. Apologies for the if this looks inaccurate. But simply put, it's a bit more than the half to reach the 1 meter for the location of this downward deflection. This is merely the half. This is the half, and this marks the downward deflection location. And there we have it. We have solved the problem. That will be all for this presentation. My apologies if this seemingly simple problem can take long to explain. However, as I have done it to the best of my ability, I hope you have learned something